Hello friends, today's video is going to be about parent functions, which is really what our unit is about, but we've kind of backtracked to some functions that don't really fit in the mold of the rest of the unit. So that's what we've been doing. We're going to move now into the more traditional functions, and this is actually an overview of what we will be doing for the rest of the year. So parent functions are a family of graphs. Oh, sorry, that is incorrect. Okay, so a family of graphs displays similar characteristics. So that might be any kind of line. So like, this might be a graph, this could be a graph, this could be a graph. And those are all part of the linear family because they all are lines. But the parent function, so we have a family, so this could be dad, cousin, uncle, sister, brother. But the parent function, the one that is reigns them all in, is the simplest function of the family. So the simplest function of the family in this case is going to be y equals x. And that is the line. So if these are our axes, the function is this line right here. And that's what the parent function for linear functions looks like. So I'm like, this one could be maybe y equals 1/2 x plus 3. This one might be x equals 4. That's a 3. X equals 3. That'll work. And this one might be y equals negative 2x plus 4. But this y equals x is just taking out all the numbers, and it's what's left. Okay, so let's look at some more specific examples, but this gives you an idea of what a family and a parent function are. So again, the first one we're going to talk about is linear, and that's what I just gave you examples of. But the linear parent function, is f of x equals x. And remember that this is the same as saying y equals x. F of x and y are interchangeable. They mean the same thing. And the graph for that is a diagonal line that goes perfectly through the center, the origin. So it goes like this. All right, so we want to look now at domain and range and all these different characteristics of the parent function for a linear function. And these words were outlined in the slides from the last assignment. So make sure that as we go through, you're understanding exactly what these things are. So the domain is where we look at the x values. So that means we're looking left to right. And on the left hand, we have an arrow pointing left. On the right hand, we have an arrow pointing right. And there are no disruptions in the middle. So that means that all x values are included. So the domain is all real numbers. For range, we're looking top and bottom. So at the bottom, we have an arrow pointing down, and at the top, we have an arrow pointing up. And there are no disruptions in the middle. So that means that our range is also all real numbers. Now for our x-intercept and our y-intercept, this is where it crosses each axis. So you want to list this as a coordinate point, so an XY point. And the point where this crosses the x-axis is at the origin, but it also crosses the y-axis there. So in this particular function, the x and y-intercept are going to be the exact same place. So we have the point 0, 0 and the point 0, 0. That's where our x-intercept and y-intercept are. The maximum number of roots or zeros. So what this means is at most, this graph can cross the x-axis how many times? And it's a line, it's a straight line, so the most it can possibly cross the x-axis is just once. So we have one root or zero, that's the maximum number. Okay, so for end behavior, this is the setup that you will always use for end behavior, no matter what. I talked a little bit about on the slide what it means in like in regular terms, but this is how it will always start. And you can actually go ahead and fill in as x approaches positive infinity and as x approaches negative infinity. So this is the exact thing that you're going to start with every single time when we talk about end behavior, and you just have to fill in these two squares. That's it. Okay, so everything else is 100% exactly the same every single time, but you have to fill in the blanks here and here. And all you do in those places is decide if y is going up or y is going down on the right side, left and right side. So let's look. So this says as x is approaching positive infinity. So that means as we go to the right, is y going up or down? It is going up. So that means it is approaching positive infinity. Now, as x approaches negative infinity, so as we go to the left, is y going up or down? It is going down. So that means it is approaching negative infinity. And finally, we want to know, is this function continuous or discontinuous? And the easiest way to look at this is to ask yourself, are there any holes in the function or any really crazy things happening? The answer is no, so it is just continuous. It's a continuous line. There are no interruptions. So the next type of graph, the next parent function that we want to look at is the absolute value function. And the absolute value function is written as f of x equals the absolute value of x. The graph of a parent function, and you'll learn all these as you graph them more, but we've already done absolute value. The graph of an absolute value function is a V shape. So it goes, the parent function goes from the origin and goes at a 45-degree angle both directions. That's our graph for the absolute value parent function. So the domain, again, is when we look from left to right, and so that's going to be all real numbers again. Our range is top to bottom, and you'll see that our y values only work if they're greater than or equal to 0. And then the x-intercept and y-intercept are, again, the same place because they're both at the origin. So we're going to have 0, 0, and 0, 0. Now, again, as I start speeding up through this video, make sure that you're understanding the words. If you need to go back to yesterday's vocabulary sheet to really understand this, please do so. All right, so the maximum number of roots or zeros for an absolute value function is 2. And this is because, like, we could have a v right here, and it would cross here and here. So we could have a maximum of 2 roots. Now remember that whenever we do end behavior, we always fill in positive infinity and negative infinity. That's just part of the answer. And then we ask ourselves, is the arrow on the right end pointing up or down? It's pointing up. So that's positive infinity. Is the arrow on the left side pointing up or down? Up. So that's also positive infinity. And finally, is this continuous or discontinuous? Well, there are no holes, and even though it makes a sharp V, that still, it doesn't stop the line. The line is still one line. So we're going to say that it's continuous. Our next function is going to be the quadratic function. So this is f of x equals x squared. That is the parent function for a quadratic function. And it makes a parabola, which is a U shape. And it looks like this. Well, that's pretty close anyway. All right. So in this case, the domain is left to right. The left arrow points left, the right arrow points right. There are no disruptions. So this is all real numbers. For the range, both arrows point up. So that means that y has to be greater than or equal to something. And it stops, the minimum y value is at 0. So y has to be greater than or equal to 0. The x and y intercept for the parent function are once again the origin. Now remember that whenever we shift these, like if I was to say, oh, my parabola is here, you'll see that it has two x-intercepts and a y-intercept, and they're all different points. So this is just applicable to the parent function. All right, so our maximum number of roots, the maximum number of times it can cross the x-axis, is 2. For end behavior, once again, we always fill in infinity and negative infinity. And then we ask ourselves, the right end of the graph is pointing up, so that means positive infinity. And the left end of the graph is also pointing up, so that will be positive infinity. And again, this graph is continuous. The next function we want to look at is the cubic function, and this sounds kind of like what it is. So we have f of x equals x cubed. Get it? Cubic function. Okay. So the cubic function is kind of I always call it the snake function, like it looks like a snake. So it does go through the origin, but it's not a perfect line. It's going to go up, and then it's going to go down. Okay? That is the parent cubic function. All right, so the left arrow point, or the left side points left and the right side points right, even though it's very slightly to either side, but that means we're going to have all real numbers. And then for range, we're looking up and down. We have an arrow pointing up and an arrow pointing down, and no disruption in the middle, so it's also all real numbers. Again, for the parent function, the x and y intercept are at the same place. Okay? And for this one, the maximum number of roots or zeros is 3. And that is because the cubic function has a degree of 3. And degree means the highest exponent that's in the equation. So this function can be altered to look like this. As long as it's got the ends going in opposite directions, that's a possible cubic function. So it can look like that. It can go like this. Yeah. There are lots of options. So the maximum number of roots it can have is 3 roots. It can cross the x-axis up to 3 times. So now we fill in our end behavior. We know that we automatically have positive and negative infinity here. Then we want to look at the right side, and that arrow is pointing up, so that's positive infinity. And then we want to look at the left side. That arrow is pointing down, so that is negative infinity. And this function is continuous. Okay, so we did the quadratic function, which is really it's called the inverse to the square root function, and the square root function is f of x equals the square root of x. And this graph is going to start at 0, 0, and then go in this direction. But if we were to plug in -1, we cannot get the square root of -1 without using imaginary numbers. And when we're plotting graphs, we cannot plot imaginary numbers. There's a whole different level of math where you can, but in this class today, we are not doing that. We're only dealing with real numbers. So we cannot take the square root of a negative number. So this graph cannot go past this anywhere. And also, you cannot get a negative as an answer, because even though like -2 can be a square root of 4, it's not the primary root, so we're not going to use that. We can't use that in our function. Okay, so this is the parent function for the square root function. And the domain for this, there's no arrow on the left side. So the right side goes on forever, but the lowest x number we can have is 0. So x has to be greater than or equal to 0. And that happens to also be true for the range, because even though the arrow points to the right, it also points slightly up, and it will go up forever and ever, but it only goes as low as y equals 0. All right, our x-intercept and y-intercept are, again, the origin. And the maximum number of roots or zeros for this equation is 1, because as you can see, no matter where we move this, pretend that's curved. Like, even if it starts way down here, it'll whoop over here somewhere, it'll cross. But it's only ever going to be able to cross once. So let's talk end behavior. We have positive infinity and we have negative infinity. And this one is a little different. So this is saying as x approaches positive infinity, so that's the right side. The right side has an arrow and it points slightly up, so that's going to be positive infinity. But the left side does not have an arrow. It stops. So as x approaches negative infinity, y is going to approach 0, and it's going to stop there. So you get 0 here because y will not go past 0 in the negative direction. Once again, or not once again, I'm sorry. In this case, the function is discontinuous, and that is because it stops at 0. It does not have arrows on both sides. Our next function is the cube root function. So you have f of x equals the cube root of x. And this one is kind of like the cubic function, except it's turned sideways. And so it's going to go, it's like an S still, but it goes this way. All right. So the domain for this one is all real numbers. We have arrows pointing left and right with no disruption. And the range is also all real numbers. We have arrows pointing up and down with no disruption in the middle. All right, the x-intercept and y-intercept are, again, both the origin. The maximum number of zeros or roots is going to be 1. Because let's say that this one curves like it did before. Well, you still are only going to get one x-intercept, and you're just going to have multiple y-intercepts. All right, end behavior. As x approaches positive infinity and negative infinity, we want to ask ourselves, what direction does f of x go? So on the right end, it goes up, and on the left end, it goes down. And this function is continuous. The next function is the reciprocal function, and the reciprocal is whenever you flip a fraction. So this is where x is going to be in the denominator. F of x equals 1 divided by x. And this function looks weird, okay? It looks very interesting. It's going to go very close to each axis, but it will never, ever touch either axis. And it goes on this side too. Sorry, that is terrible. There we go. Okay, so this is the reciprocal function. And the reason that it works this way is because let's look if we have, so y equals 1 over x. If we try to plug 0 in for x, we get y equals 1 over 0, and you cannot divide by 0. That is an undefined amount because you're not allowed to divide by 0 in math. And if we put a 0 in for y, then we would have to multiply both sides by x. And x times 0 is just 0, and this is going to cancel the x's, and you're going to get a 1, and 0 does not equal 1. So we cannot have 0 as an x value or as a y value at all, and that's why this function looks the way that it does. So our domain in this function, we do have arrows pointing left, and we do have arrows pointing right, but if we look along the x-axis, all the numbers will match up somewhere except for when x equals 0. So our domain is going to be written as x is not equal to 0 because any other number will work. And this is the same way with y. Y cannot equal 0. All right, so our x and y intercept, there actually are no x and y intercepts because in order to have an x-intercept, y has to equal 0. And in order to have an x-intercept or y-intercept, x has to equal 0. So we just decided that those are not possible with this function, so you will not have any intercepts for this parent function. The maximum number of roots or zeros would be 1, And that is only because if you were to put, like if we were to change the function to be 1 over x plus 1, then it would shift. I'm going to use a different color. It would shift to the left one, so it would be like this. But that's not a good option. Hang on. Okay, so let's say it was this way. Say we decided that there are families of graphs, so this would be in the family of the reciprocal function. And if we were to add one, that would shift everything up one. So this one would go up to here, and this one would go up to here. And so there actually would be an x-intercept. All right, so let's get rid of that and look at end behavior. So once again, as always, we put positive infinity and negative infinity in the blanks, and then we talk about each end. So as f of x approaches, or as x approaches positive infinity, so on the right end, that arrow is going to approach. So we're looking at up and down. Is this arrow going up or down? Well, it's going down, but it's never, ever, ever going to cross the y or the x-axis. So it's actually approaching 0, not infinity. It's going to get really, really, really close to 0, but it's never, ever going to equal 0. And then as it goes to the left, it's the same thing. This arrow is going slightly upward, but it's never, even in infinity, it's never going to cross the axis. And so it is also approaching 0. This function is discontinuous. See these weird things? That means it's discontinuous. And then finally, we have this word asymptote, and that was covered in your definitions yesterday. But an asymptote is a line that the function never crosses. Like do you see how this function kind of creates a horizontal and a vertical line in itself? So there's like this line and this line, which, happen to be the axes in this case. But those are the lines that this function will never, ever, ever, ever touch. And so this function has asymptotes at x equals 0 and at y equals 0. Those are the two values that will never be used in this function. All right, we've got two left. This one is the exponential function, which is f of x equals 2 to the x. Now, this can be any number in the whole wide world, but we call it 2 because if we had 1 to the x power, 1 to any power is itself, and so that's not actually going to do anything for us. But if we use 2, then we're going to see a pattern, and so that's how this works. So the exponential function, goes like this. Oops. Okay. This is the exponential function, and this is when you plug different things in for x. So the domain of this one is all real numbers. The range, if you look at it, it's never going to hit x equals 0, or y equals 0, I'm sorry. So it's never going to hit the x-axis, so that means y has to be greater than 0, and it actually cannot equal 0 in this one. It's again going to approach the axis, and it's never going to hit it. All right, then the x-intercept, there will not be one. But the y-intercept this time is at the point 0, 1. The maximum number of roots or zeros here is 1. And then end behavior, positive infinity, negative infinity. And the right side of the function is going to positive infinity, but the left side is going to approach 0. This function is continuous, and its asymptote, the line that it'll never ever touch, is y equals 0. All right, finally we have the logarithmic function, and this is f of x equals log of x. And log is the opposite of the exponential function. These are inverse functions. That means that they undo each other. So taking the log of x undoes raising something to the x power. Okay, they're inverse operations. So let's take a look at that graph. That graph is going to go like this. All right. So our domain here is that x has to be greater than 0 because it will never equal 0. It's never going to touch this line. Then the range is going to be all real numbers. Our x-intercept is at 1, 0. Our y-intercept, we will not have one because it will not touch the y-axis. The maximum number of roots or zeros is 1. And then this one actually has a special case for its end behavior. Because x is not going to go to negative infinity, we have to look at as x approaches 0, because x doesn't approach negative infinity because it doesn't go that far. So we're looking at what happens as x goes to infinity, so to the right, y is also going to go to infinity. And then as x approaches 0, so as it gets closer and closer to the y-axis, is the y value going to go up or down? And it's going down, so that is negative infinity. This function is continuous, and it has an asymptote at x equals 0. That's all for today. Have a great day.